Fellowship of the Ring uh, seminar of the academic year. And we're very happy to have Daniel Erman from the University of Hawaii, and his title is Long Live the King Conjecture.
Great. Thank you so much. Thank you for hosting this. Thanks for the invitation. These are really great events, and I'm happy to be here. Let me say, it's also nice to see so many old friends. Anyone who's seen my talks before will know what I'm about to say, but I love questions. Leap in with questions. Virtual talks, I think, even more than in-person talks, are enriched by questions and a dialogue. So jump in at any point, just turn on your mic and throw a question out there or toss it in the chat. And Michael or someone will read it to me. So please leap in with questions. Also, I'm going to be talking about joint work with a number of co-authors. I've listed them all here. A few come from not the commutative algebra world. Some come more from algebraic geometry and some from symplectic geometry. And near the end of the talk, I'll explain a little bit where that connection's coming from. All right, but let me just dive in. So I want to start with the story starts with multigraded polynomials. So what I mean here, polynomials come in different flavors. There are standard polynomials where wait, sorry, am I getting an echo?
That's pretty good. Yeah.
Oh no, that's not. There's ungraded polynomials, and then there are standard graded polynomials where homogeneous polynomials where all the terms have the same degree. And then I'll talk today about things multigraded polynomials. So I have an example here. This h over on the right is an example of a polynomial which has degree 2, 3 in like a Z2 grading. It's degree 2 in the x's and degree 3 in the y's. And each term has that property. And as you move over, we get more and more structure and kind of stronger features. You go from ungraded polynomials to graded polynomials to graded. And I'll just make an observation that multigraded polynomials show up in lots of places. I kind of have a grab bag of favorite examples. I've listed some here. If you know, blow-up algebras are often bigraded if you blow up something in projective space. Combinatorial Hodge theory, products of projective spaces and wonderful compactifications arise. Hypersurfaces in toric varieties are used in mirror symmetry to generate data and generate important examples. There's a host of places you'll see multigraded polynomials. And the kind of fundamental, at a high level, the thing I want to talk today about is how to think about the geometry of multigraded polynomials. What's the geometric picture we should associate to a multigraded polynomial ring? So I'll start with something which I am going to guess is familiar to everyone in this audience, which is the standard geometry algebra dictionary. So I'll do it for projective 3 space. So there's kind of a few ways to view it. I think of projective 3 space. I meant projective 2 space, the projective plane. I start with an action. I look at a 3-dimensional vector space where I scale by lambda, the dilation action. And that corresponds algebraically to analyzing just the standard graded polynomial ring. And from that perspective, you can take graded equations and a graded equation like this Fermat cubic kind of equation. It'll have a well-defined vanishing locus on any given orbit. It'll either vanish on the entire orbit or it will not vanish on the entire orbit. And so you can use it to analyze subvarieties of the corresponding orbit space or the corresponding quotient space, which is P2. Of course, there's a bad orbit that we have to remove, the origin here, if you want this quotient to work. But by and large, this is probably familiar to people. The standard graded polynomial ring and algebraic properties of it correspond to geometry of a projective space. If we alter the orbit structure, we get a similar picture, but some nuance starts to creep in. So I'll do maybe the first simple case, which is I'll still act by a C star, but instead of dilating, I'll act by different powers of lambda, lambda to the 1, lambda to the 2, and lambda to the 3. And if I do this, well, the algebra and the geometry both change. On the algebraic picture, what I get is a graded polynomial ring where the variables, the degrees of the variables match the exponents. So if I want equations which are going to vanish, which are going to be well-defined, or their vanishing locus is well-defined on orbits, then the natural thing to do is grade the variables as I've done it, 1, 2, and 3, and then look at homogeneous coordinates in this non-standard grading. And then those will have the right properties. And you can use this non-standard Z-graded algebra to probe the corresponding quotient. And the corresponding quotient in this case is something called a weighted projective space. If you haven't seen it before, it's quite literally like the orbits. It's just the space of orbits of this weighted action. And so it's kind of akin to a projective plane. But as you might imagine, the orbits here are a little more complicated, and these weighted projective spaces actually turn out to have some singularities. It's a little more complicated, but by and large, we have a similar picture. All right, let's ratchet it up one more layer. So now I'm going to move to a C star squared action. So here I've got a 4-dimensional vector space, and I'm going to act by 2 copies of C star. And I've written down the weights I want here. And now the algebraic picture is, well, actually everything gets more complicated. So the algebraic picture, what I should have is 4 variables corresponding to the x's, but the degrees of the variable are still going to correspond to the weights of the action. They're just going to be Z2 graded now, because I had a C star squared action. And if you look at the exponents and you look at the degrees I've set, you can kind of see how one determines the other. What we mean by multigraded equations is a little more complicated, but it's just going to be equations that are bigraded with respect to this funny grading. So I think over in the right-hand column, I wrote down, if I did it right, an equation of degree 0, 1. And yeah, it looks like that's correct. So that's an equation of 0, 1. And because it's homogeneous with respect to my unusual grading, just like with the previous examples, we can use it to probe the corresponding quotient space. Equations like this will either vanish or not vanish on each of the orbits. Now, when it comes to determining the bad orbits, it gets a little more complicated, and this is a point I'll return to in a moment. But in this case, a kind of reasonable choice for bad orbits is the ones I've written down, where either, the even variables vanish or the odd variables vanish. And if you remove those orbits and you produce the corresponding quotient, that's what's on the left column, what you'll get is what's called a Hertzebruch surface. This quotient will correspond to a P1 bundle over a P1. It'll be like a twisted P1 bundle. But it's it's a smooth variety, and it's an example of what's called a toric variety. And so there's a theorem of David Cox that every projective toric variety arises as a quotient in this way. So the kind of picture for projective space, where you took an affine space, you removed a bad locus, and you quotiented by a group action, that you can get every projective toric variety in a similar way. And there's a kind of corresponding picture where what changes is, as the toric varieties grow in complexity, the corresponding polynomial ring, what's now called the Cox ring, it gets more complicated. The kind of multigrading gets more complicated. And this series of examples is meant to kind of indicate that. All right. So here's maybe a summary of just some examples of toric varieties and their Cox rings. So I've got in the first column a toric variety, its corresponding multigraded Cox ring, marking the degrees in red. The irrelevant ideal is the ideal that gives us the bad locus, the thing we want to remove before we quotient. And then I've got the quotient. And so if you do this in a systematic way, you can go from an orbit structure or a multigraded Cox ring to a projective toric variety. Let me say throughout the talk, I'm going to primarily be focusing on the case where X is a smooth projective toric variety and S is its multigraded Cox ring. And if you're unfamiliar with toric varieties, that's okay, I think. I mean, there's a definition I could give and you could learn it, but I think the way to think of it that'll be helpful for the talk is it's a family of algebraic varieties that includes simple examples like projective space and products of projective spaces and these sorts of bundles, P1 bundle over another P1, like the Hertzebruch surface. It's kind of a class of varieties that includes lots of basic examples that we care a lot about. But it's also a simpler class of varieties and one that is open to these sorts of algebraic investigations. All right, and before I go further, I should throw one monkey wrench into this, which was in the previous example. So here what I've done, I took the previous example of the Hertzebruch surface. So the grading is the same, the orbit structure is the same. But I want to point out that I didn't really tell you how I chose the set of bad orbits. And there is a system for doing this. It comes from geometric invariant theory. It tells you kind of which orbits do you need to remove to get a projective quotient. But it's not always canonical. So this is one of the simplest examples where it turns out there are two distinct loci I could have removed to get my quotient, and you'd get two non-isomorphic quotients in this case. You know, the x on the left, that's the Hertzebruch surface I mentioned, the P1 bundle over P1. But there's also this X prime, which is isomorphic, it turns out, to a weighted projective space. And in general, this is the picture. From the multigraded Cox ring, there are, or from the orbit structure or the multigraded Cox ring, there are going to be multiple choices for what the bad orbits are. There's a way to parameterize them and understand them, but there's not a best choice always. It's you're kind of stuck with the fact that the same Cox ring can induce a number of different quotients. All right. Sorry. So I want to stick with that idea for a second. So the classical picture is we're going to relate the geometry of projective space to graded algebra, algebra over the standard graded polynomial ring. And for my own interests, I'm kind of interested in a sort of geometry of syzygies picture. That's why I copied David's book and glued it there, right? Where what you're doing is you're kind of using methods in graded algebra over the standard graded polynomial ring to probe the geometry of projective space and understand it. But you're also using geometric tools and insights from the projective space picture to understand and prove new results about syzygies or free resolutions or things like this over the polynomial ring. And it really is a rich back and forth. So I mean, again, it's kind of the theme of that book of David's is there's theorems that go in both directions. It's a whole, I mean, there's other books I could have put there. There's a whole literature that probes that back and forth. David Cox's work introducing these multigraded rings suggests we should have a similar picture where the geometry of a toric variety or subvarieties of a toric variety is in conversation with free resolutions and homological methods and things like this over a multigraded polynomial ring. The picture's a little less robust. In particular, there's kind of Cox's theorems were much more about going from the algebra side to the geometry side. And so there's a little less work in the opposite direction. But that was kind of the picture, at least that came out of his work. But I want to point something out here. There's something funny, which is it has to do with this choice of a bad locus or a choice of an irrelevant ideal, which is that the same multigraded Cox ring can correspond to several different toric varieties. And if you're interested in building an algebra geometry dictionary, this is something of a mystery. It's like a mystery. There's too much geometry. How do you build a dictionary when the same object on the algebra side corresponds to a number of different geometric objects? Now, some people in the audience may have some ideas about an answer to this. But I want to treat this as a genuine mystery because as a genuine question, because I think our main results, I'll try to emphasize, I think give a new perspective on how to think about this many-to-one dictionary. And I'll try to make that clear in some detail in the second half of the talk. All right, let me pause a second for questions. So that was kind of the opening bit on multigraded polynomials and the multigraded polynomial ring. You know, if there's some students in the audience, if people have some questions, I'm happy to go back before we move on to the next things. All right, I'll move on. So I want to talk now about modules and sheaves and eventually the derived category. So let me start with modules. So if you want to study projective space, I mean, one of the first things you do is you develop a dictionary where you take graded modules and those induce coherent sheaves on projective space. And Cox's dictionary allows for a very similar picture. So if I look at finitely generated multigraded S modules, those induce coherent sheaves on the corresponding toric variety. And I have it as a two-way arrow because, in fact, every coherent sheaf arises in that way. And so you can kind of, they're very closely related, the two sides. And so studying multigraded algebra or multigraded modules is very closely related to studying coherent sheaves on the toric variety. And so more precisely, you can even say kind of precisely what the difference is. A coherent sheaf on the toric variety is equivalent to a graded S module, a multigraded S module, where you mod out by the B torsion modules. So there's a kind of categorical sense in which this is true. If you're paying close attention, you might notice that down in the little corner, I had a reminder for myself. So I'm mostly going to be focused on the case where X is a smooth toric variety. But as in a lot of situations, sometimes you're kind of forced to, or you're led to consider varieties with mild singularities. So in fact, we've already seen an example. Weighted projective spaces have mild singularities. And when it comes to analyzing toric varieties with mild singularities, there's a distinction between varieties and stacks, and I don't want to get into it, but some of the algebraic things like this correspondence for coherent sheaves behave better if you're willing to use the word stack. So I think that's the last time I'll say that word in my whole talk. I put it in tiny text in the left to say, like, this isn't a really essential part. But for those who are kind of paying close attention, or maybe for the experts, when I talk about simplicial toric varieties later on, secretly, I'll need to occasionally invoke the derived category or introduce the derived category. And here's a delicate point because okay, so I'm going to D of X I'll use to stand for the bounded derived category of coherent sheaves. And And what this is, the objects are going to be bounded chain complexes of coherent sheaves, and but you consider equivalence classes with respect to quasi-isomorphisms between them. I mean, I think the problem with introducing a derived category in a talk is you run into this situation where if people have seen it before, the definition is not terribly helpful, right? They don't need it. If you've never seen it before, it's not so easy to kind of define in a single slide in a talk. And in fact, it probably takes a while to really get some fluency with it. So what I'll say, let me speak to the people who have never seen this before. What what I think about as derived categories, it's a way to kind of equate. If you've never seen it, it's a way to equate an object, or it's a framework for equating an object with like a free resolution or a line bundle resolution of that object. And so it kind of literalizes, in some sense, the philosophy that you might have seen in other places where you want to study a module by probing its free resolution. It provides a framework for some of those sorts of explorations. Okay, so let me give a couple examples, right? The first example is just if you take something simple like a regular local ring, then the derived category of spec of it is equivalent to the category of bounded minimal free complexes. So, it's also equivalent, if you prefer, to the homotopy category of bounded free complexes. And so in particular, every free complex is built out of R to the 1, and minimal free complexes have unique Betti numbers. And so you can think that like R to the 1 is like a basis for this category. Every object in this derived category is built in a somewhat unique way from copies of R and maps between them. If I look at like a z-graded polynomial ring, the same sort of thing is true, except here, what you need to generate all your free complexes, you need the twists of the polynomial ring. But those are like a basis. So if you're studying the derived category of graded S modules, you're essentially equating a module with its graded free resolution, its graded minimal free resolution. And these two examples, from these two examples, you can kind of see that the derived category, you can extract interesting invariants from the objects you care about in the derived category. So if you care about modules, you can still see lots of their properties after you've induced this equivalence relation. And yeah, I mean, it's kind of the graded Betti numbers, for instance, would still be visible. All right. Things get more complicated when you add geometry, and over the next slide or two, I'll try to give an indication of what happens with projective space. So, all right, so this is another bad. So sorry, this one's a bad slide. It's just there's a lot here. So the way to think of this is this: when it comes to derived categories, there's like the gold standard theorem, and the gold standard way to describe a derived category is to have something like a basis for it, something like the twists of S that we saw on the previous slide. And this was this notion, the kind of right notion, or the notion that's largely agreed upon, is that the best kind of notion of a basis for a derived category is what's called a full strong exceptional collection. And it's a set of objects which generates the derived category, and which has these very specific structures about morphisms between them. Again, I think the definition is not very enlightening if you haven't seen it before. On the next slide, I'll talk about some of the implications. But actually, here, maybe beneath the blue, there is one implication. So one implication of having such a thing is that if you have such a full strong exceptional collection, the classes of the objects form a basis for the growth-indeed group. So such a collection kind of, it acts like a basis of the category in a certain sense, in a manner that's akin to the way the free objects did for resolutions. Finding these things has been a huge topic of interest. Finding full, strong, exceptional collections or various variants of it has been major interest in algebraic geometry. Just for toric varieties, I came up with the following list. I'm probably missing some, but I think it's like 20-ish papers. And you know, the search for these things is a big topic. And I want to indicate one of the things you get from this. So let me do projective space. So in projective space, there is a classical full, strong, exceptional collection. It's called the Beilinson collection. And unfortunately, I think I wrote it backwards here, the reverse order, but I forgot to fix it, the typo. But so this is the Beilinson collection. Notice there's O, and then the other line bundles that are popping up, they're like the ones that have no cohomology whatsoever. They're the kind of gap between O and the canonical bundle, O of minus n minus 1. So you get this kind of limited sequence. I'll mention Beilinson's theorem in a minute, but let me start with the corollary, which maybe indicates why you care about this. So when you have a full, strong, exceptional collection, you get a way to represent any sheaf in an essentially unique way. So for any coherent sheaf on P2, the theorem mentioned above, the Beilinson theorem, implies that there's a canonical way to represent that sheaf as a complex, so a short complex, where the terms of the complex are sums of O of minus 1, and O of minus 2. And from that representation, you can extract invariants. You know, you get essentially like Betti numbers of O of minus 1, and O of minus 2 for any given sheaf. And those encode geometric or interesting facts about your sheaf. So I mean, at the bottom, I have two examples. One is, what's this complex look like for the cotangent bundle, and what does it look like for the tangent bundle? And you can immediately, from those representations, compute things about the space of global sections. So the tangent bundle, the corresponding complex has 8 copies of O in position 0, and that, if you know the kind of yoga of this game, that tells you that the tangent bundle has 8 global sections. With the omega 1, there's something similar. You get 1 copy of O, but it's shifted over to the right. It's in position 1, and that tells you that H1 of omega of the cotangent bundle is k has k to the 1 as one section. So having a full, strong, exceptional collection like this Beilinson collection gives you a way to represent objects in a unique way. You can extract invariants, and it kind of allows you to study objects in a different way. Yeah, and there's been a lot of work on looking for and finding these things. I'll note, by the way, Beilinson's theorem, it really, under the hood, what's going on, it amounts to the construction of the resolution of the diagonal, which he constructed. I won't get into the details, though. All right, so just to summarize on derived categories, I'll note they're omnipresent in modern algebra and algebraic geometry. You know, and it's worth asking, why did we pass from coherent sheaves to derived categories, right? I mean, I think that's a fair question. It's, if you're someone more algebraically minded like myself, you start off caring about modules. Modules are roughly equivalent to studying coherent sheaves. So, okay, so now I care about coherent sheaves, but this passage to derived categories might seem stranger. And it did for me for a long time. But I think there's a few reasons that capture why this passage is natural and is taken over in many situations. So the first point is there's no loss of information. There's what we call a fully faithful functor from coherent sheaves to the derived category. And so the derived category, it like contains all the information about coherent sheaves as a subcategory. And so if you prove things about the derived category, you're also proving things about coherent sheaves, and there's no loss of information in some sense. The second point is one that you can only be convinced of by theorems like Beilinsen's theorem and other things. But it turns out that the derived category often has better categorical properties than the category of coherent sheaves. It allows for these sorts of descriptions of generators or exceptional collections. You get these global descriptions of the category that are better and sometimes easier than you would have for coherent sheaves. And of course, the derived category is related to derived functors and things like sheaf cohomology. And as we saw in the example of the tangent bundle, representing objects with respect to the Beilinsen collection kind of demonstrates some of the properties of their cohomology. And so, yeah, that. All right. And let's see. So from Beilinsen's theorem, I want to go to the King's conjecture, which is the statement that motivated the title of the talk. So King's conjecture from 1997 said, in very loose terms, it said, Beilinsen's theorem is true for every smooth projective toric variety. So in other words, you can find a set of line bundles that's something like the Beilinsen collection for every smooth toric variety. It'll have all these great properties. And that was the conjecture. This is the more precise statement. I'll note about a decade later, I won't get too deep into this, but a decade later, Bondel gave a recipe for describing the derived category of a toric body variety in terms of line bundles, with a desire to connect it to homological mirror symmetry. And King's conjecture was very influential in the projective, in the toric geometry litter, and Bondel's description was very influential in the homological mirror symmetry literature. But there's some bad news, which is that they don't work in general. So King's conjecture, there were counterexamples eventually, and they're really fatal counterexamples. You can't alter the hypotheses and kind of make it true in a simple way. So similarly, and this was known to Bondel, the description only is kind of a perfect description if you have special hypotheses on the toric variety. Now that said, neither of these things works perfectly, but if you're willing to kind of weaken what you ask for, you can get versions of both. So King's conjecture holds if you're willing to drop line bundles and some of the features, and similarly, Bondel's description led to this coherent constructible correspondence, which is important in mirror symmetry. Okay, but the short version is, King had this influential conjecture and it was false. And what I'll do in the second half of my talk is I'll talk about our main theorem, which in some vague sense, I'll phrase as follows. What I'll say is King's conjecture is actually true. We can correct and prove King's conjecture. And the secret to how to do that was staring us in the face. It's this mystery of too much geometry. The kind of answer boils down to this fundamental question of how do you build a dictionary between toric varieties, geometry of toric varieties, and a Cox ring if it's a many-to-one correspondence. And so in the second half of my talk, I'll try to dive in and give some details about how we do that and what it gives us. All right, so if I've lined it up correctly, that's my break. Okay.
Okay, we'll break for about 5 minutes.
Great. first of all, in some sense, the first half of my talk was, or at least the ending of the first half was, the king is dead. And in the second half, I want to say, revive it and say, long live the king. And what do I mean there? So let me go back to this many-to-one dictionary where you have multiple toric varieties lining up to the same multigraded Cox string. I think one of the big ideas, maybe the big idea that I want to convey is that this is not a bug, it's a feature. This was telling us that we need to think about how to combine geometric information from all of the xi. And over the break, Arena had asked about references for derived categories of toric varieties. And I don't off the top of my head know of a great answer. There is a great reference for coherent sheaves on toric varieties. And that's one of the chapter in Cox Little Shanks's book. I think, actually, I don't remember which chapter it is off the top of my head. But it goes into great detail, the quotient construction and the features there. I'll add this idea that about this issue in the dictionary and wanting to combine the xi's. It makes perfect sense in the underived world as well, about kind of combining not just the derived categories, but the coherent sheaves from all these guys. I'm focusing a little on the derived categories because that's where the cleanest statement and the cleanest theorem is. But this overarching question of how should we combine the data from multiple toric varieties and put it in conversation with a single Cox string, it makes sense for coherent sheaves as well. Okay, so here's our main idea. The main idea behind our proof is I kind of alluded to it, but let's take all of these toric varieties that correspond to a single Cox string and we're going to glue them together to get a better object, right? We're going to think of it like gluing affine patches to get something projective with nicer properties. And so that's the basic idea. Each xi has its own category of sheaves. They're kind of complicated. They have weird buggy corners or whatever, like in my little picture here. But if we glue them together in the right way, we'll get something much prettier. So let me give the definitions. Let me explain how this is going to go. This is a bit of a busy slide, but it starts with the following. So there's something called a secondary fan, which parameterizes the varieties that arise from a given Cox string. So this has different names in different areas. You take the effective cone of X or the grade, the degrees of your Cox string where you have non-zero functions, non-zero polynomials. And it decomposes that cone into chambers. You get a chamber decomposition, and each chamber corresponds to a simplicial projective toric variety. So the kind of top picture, there's a few X's, and you get X's in various chambers. And this decomposition, it's the Mori chamber decomposition in birational geometry. It shows up in it's the wall crossing decomposition you'd see in GIT. And in toric geometry, it's called either the secondary fan or the GKZ fan. But you start with a Cox ring and you get this decomposition into regions, and the big regions correspond to that list of xi's I'd written down. The single Cox ring, you get a bunch of distinct toric varieties. So for my earlier case where I had this Hertzebruch surface and it had this funny grading, and I said there's two good quotients you could get. The secondary fan would look like this. You have a Hertzebruch on one side and a weighted projective space on the other. And those are kind of the two distinct quotients you get from this funny looking graded polynomial ring. All right. And now I can tell you, I'm going to put them together. So we go like this. We have our X1 through XR. They're all the toric varieties that are kind of come from a single Cox ring. And what I'm going to do is I'm going to choose a common cover of all of them. This X tilde. I need it to have some nice properties, but it's kind of easy to arrange. So I find something that covers all of them. And then there's a standard theorem that the pullbacks from the derived category of the pieces to the one of X tilde is fully faithful. And so in other words, we're immersing in some sense each of the individual pieces, the D of Xi's, into a single common ambient category. And that was the animation that was intended to suggest as we came in. And so the idea is we're going to define this Cox category as the image of all those things, what you get by gluing. And the X tilde is just some ambient space to make the gluing simpler. It plays no role. So if you chose a different X tilde, you pulled back to something further, you'd get the same Cox category. So this Cox category, it combines, sheaves from each of the Xi's in a particular way. Oh yeah, and that's my definition. So it only depends on the Cox ring. So I'll often denote it as the Cox category of the Cox ring, because it kind of treats each of the Xi's on an equal footing. Also, the picture is suggestive. It is almost never equal to the whole category of the X tilde. All right, so that's the definition. Let's talk about how to think about it. I mean, I think about it like gluing. It's a category where you've taken sheaves on X1 and X2 and X3, in those categories, and you've kind of glued them together. So you have the Cox category is built from those pieces, but the pieces overlap. So just to take a simple example, if you were to take the structure sheaf on X1 or X2 or X3 and you pull it back, you get the same thing upstairs. You get the structure sheaf on X tilde. So the pieces overlap, and it's their combination that we're after. And so it's a lot like gluing affine schemes. And just like gluing, you can kind of get back to where you started. If you push forward in the opposite direction, you recover the information. You recover the original category. So I'd say, you think of that like passing to an affine patch. Between any xi and xj, you can do a pull-push, and that's a Fourier-Mukai transform. And it kind of transforms the sheaf on X1 to a sheaf on X2 or a complex on X2. And so I think of those transforms as, in this metaphor of gluing, those are like the transition functions. And so the big idea is that what decox is, it's like an object in decox is like a consistent choice of a sheaf on each of the Xi's. So it's akin to studying all of the Xi's, the X1 through XR, all simultaneously. Or said another way, it's a way to synthesize sheaves from all of the Xi's. All right, let me make a few technical.
So Daniel,
Oh
we
yeah,
have a
yeah, please.
question in the
Great.
chat. Do sheaves go to sheaves under the Phi-Js?
Great. Generally, no. Sometimes yes. Generally, no. So it's a little simpler to talk about the derived Cox category. There are a few technical issues in saying what kind of the coherent Cox category would be, what coherent sheaves categories on the limit would be. But we're kind of hoping to add that in a later thing. But it's the issue is that coherent sheaves on X tilde don't always push forward to sheaves. Sometimes they have higher push forwards when you push forward under the pi i's. So did that answer the question? Yeah. Let me make a few more technical points, and if there's other questions, people can jump in. I noted here it doesn't depend on the cover. That's kind of an easy exercise. There's also a way to do it without choosing a cover if you want. It's something called the growth and deconstruction. that involves the language of lax cofunctors, which is a little more heavy duty in terms of categorical basis. But it's the growth deconstruction allows you to kind of take categories and functions, functors between categories, like these Fourier-Mukai transforms, and build a new category out of it. So you can kind of build it in that way. It's a little more close to the gluing picture. Let me see. I don't know. Other questions about this? I mean, it's a little weird, but it's a category that somehow captures the sheaves on each. So one way to think of it is this: it's like the objects of this category are like this. It's like you start with a sheaf on X1, and when you put it, when you view it in the Cox category, what you know is everything about that sheaf and also its Fourier-Mukai transforms to the other pieces. So you're like adding a little bit of extra information about how that sheaf transforms to the neighboring xi's. So it's like total information on the secondary fan. Maybe I should tackle the question, why do we do this? Why pass from all the way to D Cox? And I think the answer is kind of staring, for me at least, the answer was staring me at the face as the more I thought about it, which is it's very similar to why people pass from coherent sheaves to the derived category. So the top half of the slide we've seen before. The bottom half is new, but the Cox category has a faithful functor from each individual d of xi. And so if we can prove things about the Cox category, those will imply things about the derived category on X, or by extension, the category of coherent sheaves on X. There's kind of
So
no
Daniel,
loss of information. Yeah, go ahead.
sorry to interrupt. Question in the chat. Is the number of toric varieties associated to a given multigraded Cox ring finite or infinite?
Great question. It's always finite. It's always finite. This secondary fan is a finite polyhedral fan. So there's always a finite number, and they correspond to different. There's kind of different choices of irrelevant ideal. Yeah, let me think how to cover it. It has to do with it. It amounts to the following. You have a toric variety is defined by a fan, and so you start with just the rays of the fan, and then the question is, given just those rays, how many, am I going to say this right, simplicial fans with full support can you build with those rays? So it amounts to a finite question of subcones of given rays. And yeah, it's kind of, it's very computable too. If you start with any variety, it's not hard to compute the secondary fan explicitly. In fact, Lauren, who I think is in the audience, wrote Macaulay 2 code that produces all of these guys. Yeah, so that's a great. Was that that was the only question, Michael?
Yeah.
Great. So again, going back, why pass to the Cox category? There's no loss of information. I mean, we can, by studying it, we can recover results about derived category, or for me, even better, coherent sheaves. But it seems to have better properties. That's going to be our main theorem. And as an added bonus, it, just like the derived category, made it easier to see sheaf cohomology and things like that. This perspective makes it easier to see and compute certain push forwards, derived push forwards, of which sheaf cohomology is one example, but other things as well. All right, so let me get to the main theorem. So to get to the main theorem, I've got to tell you what the analog of the Beilinson collection is. And it's what we call the Bondel-Thompson collection. It's something that's been studied in various guises for a number of years. And it's closely related to the Cazul complex. So it goes like this. You take combinations of the variables. So I'm going to take the degrees of the variables and multiply them by allow coefficients between -1 and 0, half open intervals. And so what you'll get is like a half open polytope. It's like a half open version of the Cazul complex. So on P2, you'd have, the twists for the Cazul complex for P2 are 0, -1, -2, and -3. And those are given by various combinations of the variables. And we want the half open version of it. So we kind of leave off the last point. And so the set of lattice points you get from this construction are 0, -1, and -2. And that's the Beilinson collection. More generally, if you have some weird grading, like my running example where there was the degree -3, 1 variable, this Hertzebruch surface, if you play this game, the Cazul complex will induce a kind of different looking half open polytope, but we just grab the lattice points within it. So here I've marked in the 2 examples. In the P2 example, we recover the Beilinson collection. In the Hertzebruch example, we recover some other finite list. And there it is. It has 6 elements in this case. This set had been studied before. It was studied by Thompson in his analysis of the Frobenius summands of OX, the summands of the Frobenius push forward of O of X to higher and higher powers. It played a starring role in this work of Bondel I alluded to earlier in mirror symmetry. Each of the elements have similar properties to the Beilinson collection. So except for O itself, which is always there, the other bundles you see will never have any higher cohomology, things like that. And their classes will generate the Grothendieck group. That's actually a recent theorem of 2 separate groups of authors. I'll point out, though, there are ways in which this collection is very different from the Beilinson collection. I've highlighted 2 points here, and they're actually very related. So one is, it's not generally a full, strong, exceptional collection. Sometimes there are extensions between these bundles. And it's not always the case that the bundles are anti-Neff. So like in the previous example, the Hertzebruch, there's like a square and then 2 little guys off to the side. The guys in the square are correspond to anti-Neff line bundles. But the 2 off to the side just kind of don't. They're neither Neff nor anti-Neff. They're something in between. So it's very different than the Beilinson collection in some ways. All right. Our main theorem, I've hinted at, but let me say it. It's that this collection provides a full, strong, exceptional collection for this category. There's a couple things that you need to, there's one key definition to make this make sense, and it's the following. We have multiple xi's, and so if I want to talk about the line bundle associated to a given degree, I have to tell you which xi I'm going to pull back from to get an object in this Cox category. And the answer is that we use the secondary fan as our guide. So we look where the degree lives in the secondary fan, and that tells you which xi to choose. And the effect this has is it makes each of these line bundles anti-Neff on X tilde or on the Cox category or however you want. So there's a little kind of combinatorial recipe for how we define elements of theta within this collection. There's also in tiny text an aside about how to be an exceptional collection, you need to order the elements. And basically what that says is any reasonable order you choose will work. That's not hard. So I don't want to dwell on that. All right. So inside of the Cox category, we have these pullback line bundles. And we're claiming these are a basis for the category. They're this full, strong, exceptional collection. Oh, sorry, I didn't, this little, the red dot was meant to indicate, you look at where the Bondel-Thompson lives, and that tells you how to pull back, which chamber to pull back from. And if you lie on the wall between two, it doesn't matter. You get the same thing. Okay. So I'll really just give a sketch of the proof. You have to show that these bundles generate and that they're exceptional. So generation, which amounts to fullness, largely was the result of three symplectic geometers whose work motivated all of this stuff. Andrew Hanlon, Jeff Hicks, and Oleg Lazarev. What they did was using homological mirror symmetry, they got a new perspective on Bailenson resolution of the diagonal, and they used that to build a resolution of the diagonal for any toric variety. And so that was their kind of big theorem, and we use that as a major input in our work. We show that their resolution lifts to a kind of categorical resolution of the diagonal in a precise sense. This can all be done explicitly, by the way. I mean, Christine and Lauren and Greg and Jay have actually implemented algorithms to do this all. Okay, so that's fullness. The trickier part is exceptionality. So we want to show that these line bundles are orthogonal to each other in a particular sense, and that amounts to higher vanishing. And so I want to highlight a little bit what's going on here. I've got to prove that a certain higher X groups vanish. And objects in the Cox category, by definition, are pulled back from the various Xi's. And so the kind of vanishing we need is like this one in the second line between some pullbacks, but then a junction lets you turn an upper star into a lower star. So I kind of, by a junction, I get to this next line. And now when I'm staring at it, I've got to get a vanishing X for a line bundle with respect to the Fourier-Mukai transform of another line bundle. That's what I'm looking at. And so fundamentally, if we want to get this exceptionality, we've got to understand what's happening to these very special line bundles, these Bondel-Thompson collection guys, with respect to all of our Fourier-Mukai transforms. And that is summarized by what we call a transform lemma. So it tells us, what does the Fourier-Mukai transforms do to these special line bundles? I mean, if you look at the statement, it looks like it does nothing. It sends O of minus D to O of minus D, but they're on different spaces. So there's kind of, it's a fairly subtle statement, actually. But I'll just point out, once you understand what's happening with these Fourier-Mukai transforms, everything else is obtainable by things that were well known in the literature. So this transform lemma is kind of new, but once you do it, the vanishing you need amounts to a vanishing result from toric geometry known as de Mazur vanishing. And it boils down to the fact that you're looking at the corresponding line bundle is something nef, that's the D, minus something which had small q coefficients. And so you can get the statement from de Mazur vanishing. Of course, that just leads to the next question, which is, wait, what's going on with this transform lemma? How do you analyze the Fourier-Mukai transform of these things? And Fourier-Mukai transforms in general can be pretty complicated. You do a pull-push. Higher push forwards can be hard in general. The statement we have is there's a really delicate balance. So it's kind of only true as we've written it for precisely the Bondel-Thompson elements. If you consider any other line bundles or you vary the hypotheses at all, things break. So on the one hand, we've arranged so that these line bundles are anti-nef inside of the Cox category, and that's going to give us the appropriate R0. We're going to get the R0 that we want. But we've got to make sure it's not too negative, because if it were too negative, we'd get higher direct images. And so there is this balance. The method we end up using is a combinatorial method, a polytope method, that comes from work of Altman, Buzinski, Kostner, Wintz, Yeah, I'll just kind of mention it, but it gets maybe I'll skip that part. But anyways, the key point is understanding these lemmas. All right. So to get back to the big picture, what makes this all work? I think there's a couple answers. I mean, one is that we have to understand how these special line bundles behave with respect to the birational transforms, these Fourier-Mukai transforms. Maybe a more meta answer is that the way we've built this Cox category, it takes this special set, this Bondel-Thompson collection, and it endows it with positivity properties, making it act more like the Beilinson collection. And so we get this act of synthesizing the xi's in this way makes the connection between theta and the Cox ring more akin to the connection one sees for projective space itself. Okay, so again, I'm kind of doing philosophy for a minute. We're getting near the end. I'll just reemphasize our main theorem is that this set of line bundles is a full strong exceptional collection for this category. So what we're saying is King's conjecture was right if you expand the category in this way. If you combine the xi's, it actually was correct. And not only is it correct, it's correct in the strongest possible form. It has a full, strong, exceptional collection of line bundles, and it's the most natural analog of Beilinson's theorem you could hope for. I'll note, by the way, at the bottom, for some familiar examples, the Cox cat, for some familiar examples, the birational models, or the secondary fan is not very interesting. And in those cases, the Cox category is just equal to the original category. And so in those cases, it was kind of King's conjecture was known, like for a product of projective spaces or a blowup of P2 at a point. And we recover those cases from, as an analog of our theorem. Philosophically, what we sometimes think is going on is that this Cox category, it's like the derived category. I guess there's a typo there, but it's like the derived category of a mythical toric variety, which has a bunch of nice properties. So if you imagine that there was some mythical toric variety, X Cox, whose effective cone was the same as its Neff cone, and it had birational maps to each of these x's, and its Cox ring was the same as the Cox ring for each of the x's, then that kind of imagining would suggest the properties that you should expect for the category. So we prove we prove categorical notions, like that our category is smooth and proper and of the appropriate dimension. Yeah, it sometimes comes up there. I mean, I call it a mythical toric variety because there is no toric variety with that does this. It's in even simple examples, it's easy, maybe not easy, but it's possible to see that there's not a single toric variety that has all the properties you want. But if you kind of imagined one, it really captures what's going on a bit. And yeah. From a bigger perspective, for me at least, this solves this mystery of too much geometry, or the multi-to-one correspondence. So again, we had this picture from earlier where I had a multigraded Cox ring, which lives in commutative algebra. It was in conversation. It corresponded to a whole bunch of different toric varieties, a finite list. And then it came up briefly, but homological mirror symmetry takes toric varieties to mirrors, these objects in symplectic geometry. And so there's this giant set of geometric objects all corresponding to a single Cox ring. And if you're wondering, how do I build a dictionary between toric geometry and the Cox ring, it's kind of which xi should you look for to motivate your theorems about z to the r? I think we now have a good answer. I think the answer is, well, I mean, there's kind of I'll say it two ways, right? One is kind of the maybe not a goofier answer, which is, it goes through this mythical X Cox. The Cox category allows you to synthesize the contributions of the X's, and that's what's in conversation with the graded algebra. I think the better way to say it, the more meaningful way to say it, is that multigraded algebra things are going to give you uniform geometry of the X's. So if you want to kind of put the multigraded algebra in conversation with the toric geometry, you need to think about the Cox category perspective, where a sheaf gets spread among all the X's. And so you have a sheaf and its Fourier-Mukai transforms, or you look for geometric properties which are uniform among all of these. So for instance, all of the X's have the same dimension, and that's reflected in algebraic things. And I'll kind of end by trying to emphasize this philosophy a little more about how does the algebra correspond to uniform geometry. So that's what my last couple slides are on. I should point out, I mean, a few of my collaborators are coming from the symplectic world, and one really helpful thing in the project is that the mythical mirror is not actually mythical. So one thing you can do in the symplectic geometry world is you can kind of glue or combine Fukaya categories in a way that you can't necessarily, symplectic geometry is much more flexible, whereas algebraic geometry, things in algebraic geometry are much more rigid. So there's like a whole zoo of Fukaya categories you can define. And so we were able to define what the mirror of our mythical thing should be. And that provided motivation for the sort of properties we expected for the Cox category. I mean, our ending work is all algebraic, but having access to the symplectic viewpoint was often helpful in thinking it through. Okay, so let me end with a few things to try to nail down what do I mean by algebra in conversation with uniform geometry. So I'll start by going back to Hanlon, Hicks, and Lazarev's beautiful theorem, which is what they proved was actually the following. They proved that there is a finite free complex of S tensor S modules, which is simultaneously a resolution of the diagonal for all of the X's. So if you have a secondary fan like this with 5 different chambers, and they all have the same Cox ring S, you can find a resolution of the diagonal that's uniform for them all at once. And I think it's fair, those of us who have studied it, it's fair to say that this is the right resolution. It's not like there's a better one for X3 and a better one for X5 and whatever. This seems to be the kind of right analog of Beilinsen's theorem, and it has these beautiful uniformity properties. And so that's an indication of how, we can take an algebraic construction, a certain free complex that's motivated by that, things in the literature, and it has uniform properties for all the Xi's. Their theorem has been expanded upon in a number of papers I'll mention here. One was Michael Brown and myself gave a kind of simple algebraic proof of some aspects of their work. There's a forthcoming paper of Berkesch, Cranton Heller, Smith, and Yang that relates what they were doing and what Michael Brown and I were doing. Our big jumbo paper with 9 authors also adds to some aspects, but by and large, I mean, we have this beautiful theorem that the resolution works for all of the X's simultaneously. Let me give another example. This was a little more technical, but I saw David and Frank earlier, so maybe I'll point this at them. So okay, so if I have a secondary fan, I've got not just the maximal chambers, those are the Xi's, each of the faces also comes with a toric variety. And so I've got this kind of monstrous secondary fan sampled, labeled over there. And what we'll mean by a free monad is a complex of modules over the Cox ring, which when you look at the corresponding complex of sheaves, it's it's quasi-isomorphic to that sheaf, the sheaf you want. So it's like a resolution or something like that. What we prove in our paper is that for any sheaf, you can find a single free complex, which is simultaneously describes that sheaf and all of its push forwards and all of its Fourier-Mukai transforms everywhere in the secondary fan. So it tells you the push forward to the point, it tells you the cohomology, but it tells you the original sheaf on your original X1, but it also tells you exactly what, when you have higher push forwards for any of the chambers, any of the walls, everything. There's kind of one free complex that rules them all. And so in particular, you can get new vanishing results, not just for kind of higher cohomology, but for all the sorts of push forwards that come from the toric geometry world. Let me try to make this even more concrete. Let's take the blowup of P3 at 2 points. I'm going to take a curve in the blowup of P3 at 2 points. That's X is, this is an actual secondary fan. X is kind of the middle region. And then there are other varieties that appear in the secondary fan. And so if I have a curve in X, that will induce a corresponding curve in each of the other toric threefolds in this picture. And so we might wonder, how do we represent the curve in all those varieties? And the answer is you can do it all at once if you utilize the Cox category or this Mondel-Thompson collection. So we write down the free complex associated to this object, and then it tells me what's going on in each of the chambers. So if I want to know what's going on in the X chamber, the free modules turn to OXs, and it's those line bundles give you the resolution of your curve. If I want to know this X prime chamber, which is a flop from the X chamber, you do the same thing. You convert the S modules to X prime line bundles. And you kind of bounce around in this way. And when you get to P3, you get the image of the curve here, but there we've what's it called? Contracted some divisors. So some of the degrees become irrelevant. There's a simple recipe when you contract divisors for how to get the corresponding line bundles. What you end up with is something like this. And so in this example from the original curve, you can see that the image of the curve in P3 will be a twisted cubic. And so again, this is an example of what I mean by uniform geometry. You get a uniform free complex that describes what's going on in all of these X's simultaneously. And the algebraic methods allow you to kind of access and analyze these things in a sort of uniform way. All right, thank you. Thank you. I'll stop here. Thank you.
All right, thanks, Daniel.
Thank you.
Any questions?
I had a question. Can you hear me this time?
Yes, I can, David.
Okay, I've changed some setting. Your new category, decox, must have some property that the toric varieties don't have so that you can tell it isn't a toric variety. How does that work?
Oh man, I should know the answer better. Okay, so what's the answer? I mean, the honest answer is in examples, one can confirm, like in the Hertzebruck weighted projective space case example, we can kind of see that there's a minimal thing that maps to both of them, and that guy's derived category is too big, and anything which maps to that will be even bigger, and therefore, so we can kind of look at examples and see that actually that's the answer. If there is a kind of minimal, not in every example, but in many examples, there's a minimal simplicial refinement that maps to all the guys. And if you take that and that category is too big, then every other one, will map to that and be too big. Now, there could be I have to be careful with what I'm saying, because of course, there could be some other abstract toric variety whose derived category is isomorphic, but but not with the maps, not with the geometric maps. Did that answer it well enough, or?
Yeah, I thought maybe there was some even stronger statement, but yes.
Oh, there might be. I mean, maybe one of the things, a related thing is a question, is kind of a reconstruction kind of question, which is one we're curious about. Can you reconstruct the Cox ring from the category? You know, and a Bondel-Orlov kind of reconstruction theorem, which is a little close to that. And I think the answer is yes. I think you probably can, but we don't have a proof of that.
And just to add to Daniel's answer, I think you can show that this category doesn't have a monoidal structure.
Hmm.
And so it just automatically can't be the derived category of any variety.
I see.
That's right. That is an important way in which it is not like D of this mythical X Cox.
Good, thanks.
Any other questions?
What sort of thing can you say if you don't go derived?
Yeah, so look, it's what I think the answer is I'll tell you what I think the answer is and what the obstacle is. And I think we'll probably have this pretty soon. But I think the answer is what you want to take is just the limit over the GKZ fan. So what do I mean? A sheaf, a non-derived thing, should be a sequences of sheaves which agree under push forwards. So that should be a kind of limit object. You could say that for sheaves or whatever you want, you know. The difficulty with that is for that to be true, it needs to be true at the level of, you need to talk not just about the GKZ fan, but a kind of stacky GKZ fan. Because a lot of things I said are a little false if you move to stacks. And there's, if it's simplicial, stack versus variety, no big whoop. But when you start getting to the walls, it's not simplicial. And there we have an idea of what the appropriate stack, toric stack to associate is there, but it's kind of new. It's a new construction. So in order to say a non-derived statement like that, we would need to kind of resolve what do we mean by, a sheaf on X1 and X2 that agree under push forward, because they have to agree kind of in the right place. And it's a little technical, so we left that off for a later thing. But I think that's the answer, is it's like consistent sheaves on the XI, but consistent is hiding some scary stuff.
Oh, thank you. Very nice talk.
Yeah, thank you, David.
Okay, any more questions?
Can I follow
I have
up
a
on David's question? Can I
Go
follow
ahead.
up on David's question about the derived category Cox? Michael explained why there isn't a variety, but is there possibly some other type of space that has that it's a derived category? I mean, you're talking about, I mean, is it some in-pro stack? I mean, I don't know what.
So we've played around. Let me say it this way. First of all, this is a great question, Greg. And the first answer is there are lots of things which look like they might be right and they're wrong. So there's kind of various adding more stackiness. So what do we do? Arden toric stacks, and we non-separate. There's a lot of things that are kind of wrong. And it's easy to just see an example. So the simplest would be, what if you just glued all the varieties along their birational loci? You get some horribly non-separated gadget, but maybe that's it. But that thing's not proper. And so you lose full faithfulness. You get infinite cohomology groups. That thing goes terrible, right? So there are some kind of, what if you took a tensor product of this limit thing I'm saying, and no, that doesn't work either. So there's some kind of natural things that don't work. Surely there is some, gluing along proper morphisms instead of open immersions. There might be some answer, but I haven't been able to articulate it. And the kind of obvious things that we've tried and others have suggested don't work, except for the symplectic version, right? Where there is an obvious geometric thing that absolutely works, right? And so in some ways it's linked to a broader question, which I think is also a very interesting question of, well, wait a minute, if some of these symplectic categories have algebraic mirrors, what about the other ones, right? If they do stuff on the symplectic, if they take two symplectic things that have algebraic mirrors and they glue them, what does that mean on the algebra side? And in some sense, that was the starting point for us, but that's a much richer question that we don't have an answer for.
And can I follow up with a simpler question? You showed for projective space, weighted projective space, products of projective space, this thing was simpler. Is it true for all low rank Picard groups, right? Those are all examples where the Picard rank is the most too. Is it true for everything that has low Picard rank?
Wait, I mean, for Hertzebruch surfaces, it's different. I mean,
I see. It doesn't work for Hertzebruch surfaces.
Hertzebruch surface, yeah, it just, so it was just a blow up with 1 point. No. So it's generally, it's very rare that they're the same. It's essentially, in fact, it's classified somewhere where we may even mention, I forget, it's one of my co-authors who's here, remember it? I think we cited a classification of when they're the same in our paper, but I don't remember what it was.
Is it not when Neff is effective?
Is it just when Neff is effective? Actually, that's probably right.
I don't know.
No,
But
I
it
guess
might
it's
be.
a little more general though, because the blow up at 1 point also.
Yeah, that's the one I don't know about.
Okay.
Certainly Neff is effective implies that. Yeah.
Yeah, that's products of projective space. It's not so exciting.
Yeah.
Right. Any more questions?
Daniel, does the reference use for derived categories, chapter 5 of Kotzel Schenk, does that talk about derived categories?
No. It only talks about coherent sheaves. I don't think there is one for derived. I don't think there's a good one for derived.
Okay.
I think, unfortunately, I think it's a good point, but that gives a description of the coherent sheaves. And so if you're a little familiar with how to go from the abelian category to the derived category, that would tell you how to algebraize it. But
I just went to try to find the chapter number and was like not sure that I had found the right one.
no,
But
that's absolutely right. I don't think there is I mean, Greg or Michael or someone can turn off their mic if I'm wrong, but I don't think there is a good one. For derived categories.
All right. Any other questions? Okay. Well, thank you again, Daniel.
Thank you. Good to see you all.
Thank you.
Daniel. Thank you.
Bye-bye.